Hello, everyone. So what I want to do, excuse me, is prove Fourier inversion. So we proved last time Parseval's uh, theorem that the Fourier transform is an L2 isometry on L1 intersect L2. So now I want to prove Fourier inversion, and like before, we're going to do this for functions living on Rn. And then we'll talk about how to define the Fourier transform on functions that are just L2. Because as I mentioned, the integral defining the Fourier transform doesn't really make sense unless function is in L1. Okay, so let's begin. So let's say Gj is the following. And we computed the Fourier transform of Gj. It was just j to the n e to the, j to the n over 2 e to the minus pi modulus x squared. So if I plug in x minus y, I get the following. And you'll notice that this is the same thing as g hat of y minus x, which is, well, Gj inverse Fourier transform. So we haven't actually proved it really is the inverse Fourier transform, but I'll still call it the inverse Fourier transform. It's just a Fourier transform with minus plugged in. Okay, so this is something very good to know. And I'm going to call this, well, this is going to be equal to this right here, f square root of j, which is the function where you convolve, where f square root of j, remember, is a function where you convolve it with f, let j go to infinity, and we have convergence to f in LP, in particular L2. So, right, so remember, we talked about this extensively last time. As j goes to infinity, this is just going to be f, converges to f in, sorry about that, in L2. Okay, right, so maybe it's a little confusing, so I'll get rid of this here. But, okay, so let's actually put this to good use, and this is extremely important. Let's actually put all of this to good use. Okay, so because we have convergence in L2, we can pick a subsequence converging almost everywhere. So just do exactly that. Now, actually, as j goes to infinity, we do have almost everywhere convergence thanks to the Lebesgue differentiation theorem. If you don't know what that is, that's fine. We'll discuss it. We'll prove it using the Hardy-Littlewood maximal function. For us, it's extremely important. It leads to the Calderon-Zygmunt decomposition, which is the cornerstone of like modern, Fourier analysis. Okay, so f of x is going to be this limit almost everywhere. Let's dump in the Fourier transform. Okay, so remember I mentioned a second ago, or maybe a minute ago, that this whole thing here, sorry about that, this whole thing here is equal to jk inverse Fourier transform x minus y. So let's plug that in. Okay, this is exactly, this whole integral here is exactly inverse Fourier transform gjk of x minus y. It's just a Fourier transform without the minus sign here. Now let's do something clever. This clearly here is an L1. This is just this Gaussian for fixed jk. The f is assumed to be an L1. We can use Fubini's theorem So I'm going to break this up into e to the 2 pi I x dot u right here. This is going to be e to the 2 pi I minus y dot u, which is minus u dot y. This is a minus here. Okay, so now I do the y integration first. And we get exactly, here is the Fourier transform of y with u plugged in. Just bring the minus outside. And this is exactly, well, the Fourier transform of this product here with minus x plugged in, which is, of course, by definition of the inverse Fourier transform, just the inverse Fourier transform with x plugged in. Okay? So what I need to prove, because as k goes to infinity, this whole mess here is f of x for almost every x, I need to prove that as k goes to infinity, this converges to gjk f hat whole thing inverse Fourier transform of x. Sorry, this needs, as k goes to infinity, this whole thing needs to converge to f Fourier transform inverse Fourier transform of x. So let's do exactly that. So to do that, I need to know that gjk f hat converges to f hat in L2. And this is fairly trivial. So first of all, what is gj? Well, it's this here. And when j goes to infinity, point-wise, this is just e to the 0. E to the 0 is 1. So not much to that. So we just need to check that we have a dominator when we look at this expression here. Well, just smash in absolute values. This is exponential, bounded by 1. So it's f hat modulus, 2 times f hat modulus. Square it, it's 4. So really not much to that. So we can use dominate convergence here, and we get L2 convergence here. So let's put that to some final good use. Okay. So, right, remember the goal here, maybe I'll write that down. So it's enough to show that this here converges to f hat inverse hat, well, in L2. Because then we can do something, we just do usual, take a further subsequence, and we get point-wise almost everywhere convergence. So let's check exactly this. And here we're going to use the isometric property of the Fourier transform. So we want gjk of f hat with minus x plugged in, because that is what the inverse Fourier transform is, minus f hat with minus x plugged in. Well, just change variables, u equals minus x. So it gets rid of the minus. Bring the Fourier transform outside. It's trivially linear. Okay. Now let's use the L2 isometry property. We get this here, and we just proved, using dominate convergence theorem, that this here converges to 0. Okay. Should be k here. But anyway, so as k goes to infinity, this converges to 0. Okay. And again, that's exactly what we need to do. So maybe just to recap here, for almost every x, f of x is going to be this limit. This limit here, we compute it to be gjk f hat inverse Fourier transform. And we just proved using dominate convergence theorem and the isometric property of Fourier transforms that gjk f hat inverse Fourier transform converges to f hat inverse Fourier transform. And hence, for almost every x, f equals f Fourier transform, inverse Fourier transform. Okay. Right, so this got cut off, but this is, doesn't seem to like that. Anyway, that's good enough. Right, okay, so let's talk about the, don't know why this is here, but okay, so let's talk about the L2 Fourier transform. 1 second. All right, so I need a lemma talk about the L2 Fourier transform. It's a very trivial lemma, but it's good to prove because it tells us how to extend the Fourier transform from L1 intersect L2 to L2. And again, remember, the issue is for an L2 function, the integral defining the Fourier transform is sometimes not defined. It just sometimes the integral does not converge. So we simply cannot define the Fourier transform on L2 by the integral. But that's okay. We can do the next best thing. We can extend it from L1 intersect L2 to L2. So let's say we have a linear map T from X to Y. X is normed space, Y is a Banach space, and on a dense subset, T is isometric. Then T uniquely extends to an isometry from X to Y. Okay, so pick an X, pick an XK and U, with XK goes to X. We can do that, U is dense. Let's show that TXK is Cauchy. Well, just pull out the T of xk minus xm. This is an isometry on U. Xk and xm are both in U. So actually, sorry, I want this to be a subspace, a dense subspace. Okay, so because it's a dense subspace, right, xk minus xm, this is in U. T is an isometry on U, so T goes away. Well, xk is convergent, hence it's Cauchy. So Txk is Cauchy, so it has a limit, and define T tilde of x to be this limit. So first of all, I'll leave this for homework. This is easy to check. This is independent of whatever xk you pick converging to x. Okay. Second, this is linear and it's an isometry. That's easy to prove. Third, it is an extension in the sense that if x is in U, T tilde x is Tx. And last but not least, T tilde is the unique linear linear isometry satisfying, I think I spelled that right, 3. Okay, so let's put this abstract mumbo jumbo to good use. Let's say x is y is L2, L2 is complete, T is a Fourier transform, and U is L1 intersect L2. I mean, that's trivially dense. It's a dense subspace of L2. That's pretty easy. I mean, you have functions C infinity with compact support is dense in L2. But certainly L1 intersect L2 is dense in L2. All right, so by definition, and this is nice because this is saying this is the only way to define the Fourier transform on L2. The uniqueness property says you cannot define it in any other way to coincide with the Fourier transform on L1 intersect L2. So pick any fk in L1 intersect L2 converging to f and L2. Okay, then the Fourier transform of f is defined by this here. And define the inverse Fourier transform to be the Fourier transform with minus x. That's obviously a well-defined L2 function because f hat is a well-defined L2 function. Okay. Well, we proved that this is an isometry. And again, just change of variables gives me f. The inverse Fourier transform is an isometry. So this is a little bit, you have to prove something. So maybe let's prove this real quickly. So I'll give something like this for homework. And the proof is not going to take too long. And you really have to use the definition. All right, so you have no other choice but to use the definition. Well, let's use K. Okay. Okay, so right, so fk converges to f in L2. So as a linear isometry, certainly Fourier transform is bounded on L2. So that means f k hat converges to f hat in L2. And that means, so go back here. So we have two perfectly well this is perfectly well-defined L2 function. We can apply the inverse Fourier transform. And we know that's an isometry. So it's certainly bounded on L2. So we know from this that this converges to f Fourier transform, inverse Fourier transform. Okay, well, what is this equal to? Well, almost everywhere, this is going to be equal to fk. So in L2, fk converges to f hat inverse hat. Okay, but what does fk also converge to? Drum roll, not needed, f. So the conclusion is f equals f hat almost everywhere. Okay, so Fourier inversion is true. So the moral of the story is you have to go back to the definition of the Fourier transform when you prove something about the Fourier transform on L2. Okay, so let's get back to this here. Okay, so what this tells me is that we have an invertible isometry on L2. Whenever you have an invertible isometry on a Hilbert space, that means it's unitary. So we have a very nice canonical unitary map from L2 to L2. This is extremely useful in operator theory, PDE. I won't really push this too much. So I do want to discuss one application to PDEs, and we're going to be very informal here, we're going to be a little informal. You can really make this more rigorous by using a theory of distributions and talk about the Fourier transform of a distribution I don't really want to get into that. You'll definitely learn that if you do PDE theory. Okay, so let's take F and C infinity compact support. Let's see what happens when we take the Fourier transform of the derivative. And this is why this is so useful in PDE. Well, I'll just plug into the definition, integrate by parts, and let's take a limit. This is a Riemann integral. Just do usual integration by parts. F is C infinity. It has compact support, so plug in R for large enough R. This thing is going to be 0. Okay, and you integrate this, you differentiate the exponential. So it's minus 2 pi I x. Remember, x is constant here. And you just get the Fourier transform here. Okay, so the Fourier transform of a derivative is 2 pi I x Fourier transform of f. Take two derivatives, do the same thing twice. Okay, and for PDE, we want to do this on Rn. So I don't want to dwell on multinomial notation, but if alpha is a n tuple of non-negative integers, define, well, usually it's, depending on which book you read, it's dx alpha on bottom or just partial alpha for shorthand. So you're going to just do the x1 derivative alpha 1 times, x2 derivative alpha 2 times, all the way to the xn derivative alpha n times, and define the norm of alpha, so to speak, to be alpha 1 plus alpha n. Add all these up. Okay. But anyway, so let me get rid of this here. Okay, so same kind of argument gives me that the Fourier transform of this partial derivative operator is going to be 2 pi I to the norm of alpha x to the alpha f hat. So let me do a really nice, well, so this is probably most often used. I should mention this is really the beginning of the area called pseudo-differential operators. I mean, that, sorry. Yeah, I don't want to get into that really. But anyway, so if we apply this to the Laplacian in particular, so remember the Laplacian is just the sum of these partial derivatives. There should be a squared here. And this is going to be, well, apply it to each one, minus 4 pi sum here, xj squared f hat of x. It's just going to be 4 pi modulus x squared f hat of x. So let's see informally how to do this. How do you solve PDEs using this? So this is a very classical PDE. I forget what the name of it is, but so let's solve this. And we're going to be wishy-washy doing this. Again, you can make this very rigorous using the theory of distributions and the theory of weak solutions of PDEs. That's very important. I use it in my research a lot, but we don't have time to do that. So, all right, so let's take the Fourier transform of everything. So minus gets rid of this minus, so it's 4 pi squared modulus x squared u hat of x, u hat of x, f hat of x. So I guess I'll throw in x's here. Not that it matters much. Okay, so we can just solve for u hat. U hat of x is f hat of x, pull out a 1 over 4 pi squared, 1 plus modulus x squared over 2 pi. So I'm going to rewrite this. Well, sorry, I'm going to take inverse Fourier transforms, assuming I can, assuming everything is nice and, you know, L1, sorry, nice and L2, I mean, again, I'm being informal here, but right. So for homework for U and V in L2, sorry, this should be, yeah, let me get rid of this here. Well, that's not going to help. So really, this should be the whole thing Fourier transform. Okay, so the Fourier transform of U convolved with V is a product of the Fourier transforms. Okay, and it's just Fubini's theorem, really. So you do Fubini's theorem, and prove it on. So you use Fubini's theorem for U and V and L1 intersect L2, and then you do this approximation argument by L1 intersect L2 functions to prove it for L2 functions. Okay. Right. So, right, you use this fact here. I'm going to define B to be the inverse Fourier transform of this function, well, 1 over 1 plus x squared over 2 pi. I'm putting a dot here to indicate that this is my function. So the point here is that the Fourier transform stick in an x here, and you do this a lot in analysis. So the point here is the Fourier transform is going to be 1 over this function exactly that we want here. Okay, so this is really f hat b hat inverse Fourier transform, which is Fourier transform of the whole thing inverse, which is just f convolved with b. I forgot the squareds here, but that's all right, not a big deal. Okay, and you can prove, it's a little bit tough. I mean, there's some work to be done, and if you want to know where a good place to prove this, I like this book a lot, actually. I think, and Professor Bachanu can vouch for this. So this is proved in partial differential equations by Lawrence Evans. It's very easy to read. It discusses a lot of good PDE in here. This is my go-to for PDE theory because I'm doing that right now. Yeah, and this is actually in there going from here to here. And you can prove that this is going to coincide with the following. Okay. Right. Okay, and so it's, I mean, it's a little tricky because you don't exactly know what B is. So it's a little unclear, you know, what this is. I mean, I guess B is the inverse Fourier transform of this, and you have to compute that, and you can actually compute that in higher dimensions using complex analysis. So to do Fourier transform calculations like we did, Fourier transform of a Gaussian is a Gaussian, you do use, you know, contour integration quite a bit. Okay, so that's it for now. Right, so yeah, actually I do want to mention, I was going to say something about, right, about pseudo-differential operators. So in this sense, this is going to look a little wacky, but what you could do is you could say you could, at least for you know, very nice functions, you can define derivatives purely in terms of the Fourier transform. Take the inverse Fourier transform of everything here. sorry. So I don't want to put an X there. So, right, inverse Fourier transform everything. So you can write any partial, or you can write these partial derivative operators as an inverse Fourier transform. Okay. So, right, and this is the start of the area called pseudo-differential operators, where you define operators very similar to this that extend the this formula, so it kind of extends the idea of a differential operator. Hence, it's called pseudo-differential operators because they're basically the same thing as this. They're defined in terms, they're similar, defined in terms of Fourier transforms, but they're really not differential operators. So yeah, and if this intrigues you, this is a very, very deep, useful subject. But if this intrigues you, just send Professor Alexandrova an email. She's the department expert in pseudo-differential operators. She uses it to study objects in quantum mechanics, magnetic Schrodinger operators. So yeah. So all right. Hopefully this was interesting. And yeah, again, this it really should be. Yeah, if there's any confusion here, just maybe cross this out. This is going to be U convolved with V Fourier transform. Right. Okay, so long. Take care. Until next time.